43. So again, some electrical aura is given. Of course, we can describe that either using electric field or electric potential. Here we have some information about the electric potential, only some information. Okay, let me draw which information is given. Okay, I'll probably draw it here. So let's say we have this line, right? And points of this line is at 30 volts of the electric potential. Then there is this line, and points on this line is at 10 volts. And then there is another line over here. So these points are at negative 10 volts. Then there is a proton. Yeah, okay, maybe I should write. So then a proton flies. A proton flies through this field. Right. So let me draw some arbitrary trajectory. So let's say this is a proton flies through this. So plus, that's our proton. Then there is an additional piece of information about its speed. Let me label this point, for example, as point A. Okay, let me use blue. So let's say this point is A, and let's label this point as point B. 2 points. And we have information about the speed, basically magnitude of the velocity at point A. So we know that magnitude of velocity of the proton at this point is v sub A, and that value is v sub A 50,000 meters per second, 50 kilometers per second. It's definitely less than this by an order of magnitude, right? So what we need to find? We need to find its speed at point B. So let me draw this. So it will be v sub B, and I put a question mark. So that's the problem. So we need to find. Okay, it looks like I need to change marker soon. So again, 2 approaches now we have. Equally strong, equally powerful force approach or energy approach. Which approach should we use here? Again, let's look at what is given. We have which information about the electrical aura is given. Not much, actually. We only see what? 3 equipotential lines. We don't know what is between them, right? So only information about 3 equipotential lines, right? And of course, since we want to find velocity at point B, which is on one of the equipotential lines, so we can easily connect these numbers, electric potential, with the potential energy. So we can get easily information about the electric potential energy. And if we can easily get information about the electric potential energy, and we need to find some information basically about kinetic energy, right? So we can use conservation of mechanical energy approach. Here it sounds like is a nice approach. And of course, I know it will be the best approach. Because in this case, the force approach, where you have to use electric force, electric field, in this problem cannot be applied. Because we don't have information about the electric field. And actually, we cannot get information, enough information about the electric field in order to apply that method. In this case, like on Monday or Tuesday, we will see that based on this picture, we can only get the average value of the electric field. for example, based on these three equipotential lines, we can get only the average value of the electric field in this region, but average value is not good enough for us in order to get exact value of the velocity at that particular point. So we just don't have enough information in order to apply the force approach in this case. In this case, only energy approach can be used. All right. Okay. Once we justify that, and actually now application of energy approach in this case for you, it shouldn't be difficult for you. Similar steps. Right. So, all right. Again, let me write. It's option 2. So, energy approach again. So again, I will start with just comparing energies, but now at point A and point B. Instead of using A capital and B capital, I use A small, B small because it's easier to write. Right. Okay, and then explicitly kinetic potential. So Ka plus UA equals K sub B plus potential energy at point B. And again, I told you actually in a problem like this, as I told you, a few students on the final exam got stuck and they didn't know how to move to the how to connect information about the electric potential and the electric potential energy. But of course, you just need to use that. Okay, let me even frame this, right? So now, of course, we have to use the same. So we're going to insert over here the fact that U equals Q times V, and let me again frame it. Can we dump any of these terms? Actually, no. Unfortunately, or fortunately, none of these terms is 0, so we have to drag all of them, right? And the unknown, where is our unknown? V sub B. So that's where our unknown, right? So now let me move this term to the left-hand side and isolate it, right? Separate it. So it will be U. You know what? I just said nonsense, right? You realize we need to find velocity, not the potential. Damn it. I thought about the potential. Of course, since we need to find velocity at point B, of course, our unknown is in K sub B. And you quietly listening to my nonsense, right? So now let me erase it. I need to also erase this part from the video, right? So that I wouldn't embarrass myself. No, it happens. Right. All right. So that's where our unknown is. Right. Okay, so it will be, okay, I will move this to this side. So it will be 1 over 2 mvb squared equals, all right, and that term, of course, I will move to these guys to hang up. All right, so 1 over 2 mva squared. So I just wrote this now, plus q v sub a, so it's this term. And of course, this term will go to that side with minus. So now minus qvb, v sub b, minus qv sub b. Okay, so now the next step, we just need to show explicitly our unknown. Okay, I see that there is some. Okay, Sophia, I see the question, is there an example of when the force approach will work, but the energy approach will not? Yeah, I'm sure that we can come up with a situation like this, right? I just cannot recall when I saw an example like that, but I'm sure that it can be constructed, right? Again, it depends. Basically, it can be, for example, your experimental setup, right? So let's say you created electric field and you have only, for example, voltmeter, and you can only map a few equipotential lines. And let's say using voltmeter you map, so here you have 30 volts, here 10 volts and minus 10 volts. and that's what you have. You don't have anything else. You don't have information about the electric field. So, and then proton, I know, solar wind, proton flies through your system, right? And you want to predict the velocity. So it's just a possible experimental situation. I'm sure that you can come up with an experimental situation where maybe electric field is given. Or maybe you manage to steal from, I don't know, from neighboring lab only that information about the electric field, and you want to do some calculations for them in order to guess what they're going to get. I'm just blabbing, right? I'm just telling you, yeah, it's possible to come up with any possible situations. Maybe there are situations where you don't have enough information for any of these methods. In that case, you will have to, I don't know, guess. It's life, right? There is life in the research. You can come up with any possible situation. It depends on which equipment you have. Does your equipment work properly, and so on and so forth, right? And every time you have to juggle all everything in order to see what work, what doesn't work, right? So yeah, I'm sure that you can come up with an example where energy doesn't work approach, and of course will have to be used. All right. Okay, so now I just want to clear our unknown from any factors in front. So I'm going to, let me move this information slightly higher, minus 10 volts. And I just need to multiply the whole equation by what? By 2 and divided by m in order to clear this factor. I mean, in order to clear my unknown from any factors in front. So this m will disappear, 2 will disappear, this is the same. Here we'll get 2q divided by m, so on. Right, vb, and of course I will take a square root sign. I will write a square root sign immediately. So this will be just va squared. Then q, of course, I will factor out. So it will be plus 2q divided by m, and v sub a minus v sub b. So that's basically the answer, right? In terms of symbols. Okay, let me make sure that I got what I supposed. Yeah, that's correct. So now you can plug numbers. Of course, I'm not going to do it. Charge of the proton, it's a positive 1.6 times 10 to the power of minus 19, the same as charge of an electron, but with plus. Because a few times on the final exam, I remember students were asking, so what's the charge of the proton? The same as electron, but with plus. So if you plug it, you know what? There's only one thing which you have to be careful. I just now realized that I need to mention that. Look at this parenthesis. Let me write in terms of numbers. VA 30. So this will be 30 volts. Okay, I don't like this bracket. Let me without this bracket. And then minus from the formula. And the value of V sub B minus 10 volts. So we're going to have minus 10 volts. Don't forget about these two minuses. Minus 10 volts. So, of course, it will be equal to 40 volts, right? Okay, so now I will just write down the answer. So it will be 1 times 10 to the power of 5 meters per second. So it's a 100 kilometers per second. Here we had 50 kilometers per second. Now it will be 100 kilometers per second. So proton got accelerated as it moves along that trajectory.